one formula sheet, one side only. And if I were you, I would take the one that you have for test 1, and then continue on that half page. There will be practice problem posted. I will be out of the country, and I cannot give you a help session or study session the night before on Wednesday. I'll be on my way to Berlin, Germany, so that's why the class is used to give you a test. What's the point? The point is you need to maybe make use of Mike's additional office hour that he will post on Wednesday, just so that you have time to ask questions, but there will not be a help session because of my travel schedule. Any question on test 2 format? All right. So reading is kind of tabling off in the chapter of pipe flow, session 5 of chapter 8. There's handout posted in addition to the energy equation, another page on nomenclature, just all this symbol of Q dot, and velocity and so forth. So it may be worth for you to just take a look at that as a visit. Homework is a little on the heavy side, 4 problems, but it's not difficult problems. So 2.5 hours, the most you expect, and Mike will post the numerical answers, not the solution, obviously, in the assignment on Canvas, so you can check your own work. Problem in chapter 8, I'm not going to touch on it. They're pretty fundamental use of Moody diagram. And energy equations on chapter 5. 4 more problems still for next Tuesday, and that is all the homework you see prior to test 2. All right? Any questions before I start? Questions? So the quiz last time, I want to go over that, and I also want to revisit the energy equation before I do a deep dive using an overhead from your handout. That's the energy equation as we will intend to deep dive, at the end of which we will be very precise as to what really represents this H sub F. That's the whole intent of spending almost half an hour on it. The H sub S, as we have discussed, as a repeat, represent the shaft work measured in length, height, and turbine is plus, pump is negative. And we will show you today from the energy equation for control volume, assuming no heat transfer, how this equation can be derived from the energy equation. That's the intent of what we want to do. And for the quiz, you will ask 2 parts. The first part relates to actually what is the physical meaning of Ws over G. It's posted in a very different way. First part is tell me when the equation of energy, or even Bernoulli, because they are all in the same form for this, just P plus half mole V squared plus OGC. What is the physical meaning, physical interpretation of a term that has pressure over rho, which by itself is by no means transparent. No, it's very difficult even for me to try to interpret what is the physical meaning of a term of pressure divided by density. So how would you start? Yes?
Do you look at the other term as 1
you go to the other term. That's the main takeaway that I hope you to get a sense of. So in this case, which other term here will look something that you're comfortable with? Half v squared. And we went through that in class prior. Just as a reminder again, kinetic energy is half rho v squared of such v squared is nothing but same as the half is not significant. This is all looking at unit. So half mv squared, which is energy divided by mass, will give me a unit of v squared, which then the answer for this is what per unit mass? Energy. You've seen it before. I just hope you will remember that. So when I have the equation of energy of Bernoulli expressed it in this form, it represents energy per unit mass. Okay? So the potential energy can be read as potential energy per unit mass. Kinetic energy is kinetic energy per unit mass, etc., etc. So you get it for part A. So the answer is none of the above. All right? Part 2 is a twist, just a little bit more to this same equation, of which now I'm putting in the form of dividing everything by G. Same as part 1, now it's divided by G. Any ticker? How would you read that in terms of physical interpretation? Length. It is length. But the answer gives you choices from A to D: energy per weight, energy per volume, energy per time, or none of the above. Using the same approach of what we did in part 1, how would you answer part 2? Anyone else? Yeah?
Energy per weight.
Energy per weight, how do you get that conclusion? From part 1? Yeah?
See, since we basically multiplied mass on the bottom by G, you can say that mg is force, so then you can say energy per weight.
That's correct. So let me point it out for those who do not see that. So what we are asked to do is to interpret the physical meaning. Again, the half in the denominator is inconsequential. This is all unit interpretation. This, based on part 1, is energy per mass, which is the conclusion of part 1. With the exception now, I multiply the denominator also by gravity. So what is mass times gravity? Weight. So this is now interpreted as energy per unit weight. Do you see that? Let me make sure you are comfortable in doing this type of interpretation of the physical meaning of the term in the equation. And this is important if you can appreciate what has been done. When I tell you a pump here raises the head, a water pump raises the head of the water coming out of it by 100 feet, 100 feet of head. What does that mean to you? That directly relates to the amount of energy transferred to the water per unit weight as it goes through the machine. So it's indicative and related to the amount of energy transferred to the water via this equation, which is important to close the loop for the gasoline problem as well as the fire hydrant problem. So they're all coupled. Yes?
I was just wondering, so would the unit of this pressure by itself be energy over volume?
Pressure, in which form?
If it was just pressure by itself.
pressure by itself, yeah, you can see it that way. Yeah, but it's not very conventional, right? Yeah, that's a fair statement. So what all this ties into is given the head rise due to a fluid machine, a pump or turbine, this X of S, we can tie that in to the power through this equation of m dot mass flow rate times the specific work, right? Where specific work in what we have seen is given in here by this equation. How this comes about and how the H sub F comes about is what we're going to do now. We're going to do a deep dive into the forest. In a time you may not see the tree and you may be confused. I want to take a big step to close the loop. The energy equation plus this power equation is all you need to tackle any fluid system. Meaning give me a flow rate, give me a geometry, size, length, the fluid. I can tell you how much frictional loss occur, and I can tell you how big a pump I needed to move the fluid. So when we're done with today's lecture, you'll find out that to move that gasoline over 9 miles take a lot of energy. A lot of energy. And that's our intent. Okay? So I think that's a backdrop. Let me also review and recap back to chapter 5, the so-called Reynolds transport equation. But before that, this is your thermal review. First law, okay? For a system, this is your first 2 weeks of thermodynamic this semester. Classical system, piston and cylinder. And by a system, I refer to a fixed mass. You've seen this, right? Not only in Thermo 1, but even in 21-24. That's what we call a system. So the first law tells me how this system interacts with the surrounding by way of heat, Q, and work. Those are in actual energy unit, BTU or Joule. So the first law, as you have seen from system, from your thermal, tells me how the work and the heat will result in a change in what we call total energy. Total energy, right? Of which this capital E consists of 3 components: kinetic, potential, and what's this U? Internal energy. Very good. Is this new to you? No? I think you have seen this, I hope, many times. On a per mass basis, we have now the small e per unit mass, and everything now is written in terms of per unit mass. So that's just a quick review of Thermo 1 by way of a system. Any questions before I go on? So in fluid, we look at it a little differently. I don't know how you have handled that in your Thermo 1. You need to transfer this system equation to a control water so you can work energy equation for a device that has flow coming in and out, like a turbine, like a pump, like a boiler. Not a system, but it consists of flow coming in and out, a gas turbine, an IC engine, etc., etc. So that's what we are tasked to do now. And the way we'll approach that, may or may not be the same as what you have done in your thermal, but they are consistent, is in fluid. I'm going to go back to, in chapter 5, the so-called Reynolds transport theorem. And let me remind you the form of that transport theorem. It's been more than a month when you've seen this equation, so it's a good time to just revisit it in the context of energy equation. So this is a general transport theorem due to Reynolds, of which allow us to take a system equation and make it into a control volume application. Can someone remind me what this somewhat intimidating integral over a differential area that has the density and a dot product of V dot N? What does it really mean? Say it again? Very good. It's no different than rho V A. Remember all that? So what's the significance of the dot product?
Direction.
Direction cosine. Yep. It tells you the velocity must be in what relationship to the area? Perpendicular. What's the significance of the integral over a differential area? When is that needed? When is that needed? Don't remember? No one?
Pure velocity is not uniform.
When the velocity is not uniform, not in the boundary layer, not in the pipe flow where the velocity is parabolic, like the homework you have done. So that's just a reminder, this is nothing new, but it's been a month, so I think it's fair for me to revisit it so that you can get more comfortable with this equation for the second and last time. And what we have done prior was use this equation for 3 times. Which 3? Continuity, momentum, and then lastly the angular momentum, which we have very little homework due to the lack of time to deal with that. And today, we're going to finish this off by looking at how I can use the transport theorem of Reynolds to come up with the energy equation specifically for pipe flow. And it's in a form different than what you're accustomed to see in your thermal classes in parallel with this class. So for continuity, I won't go through the derivation. We set beta equal to 1. Beta is the quantity per unit mass. So for continuity, beta is simply 1, and out comes the continuity equation. Momentum, the beta is the vector and it's the velocity vector in 3 directions, I, J, and K, or X, Y, and Z. Angular momentum, velocity cross product with the radius. Remember all this? Question before I start? Now we're dealing with energy. Any guess as to what you will set the beta to in reference to what we did in your system all the way down in here? Something that is per unit mass. Anyone want to guess? Beta 1 for continuity, beta equal to the vector V for momentum. What do I want to take beta to be, which is the quantity per unit mass, so that I get the energy equation. The answer is on the board. Huh? Internal energy only? Only this guy? Total energy, you want everything. You want internal, kinetic, and potential. And the energy equation is a scalar equation, have no directions, unlike momentum that has x, y, z. So that is a review of your thermal and a review of Reynolds transport theorem. So now we are ready to do the deep dive, of which I'm going to take all this and merge it. So I'm going to show you how the system equation here for the first law can be transferred via the Reynolds transport equation by setting beta equal to the specific total energy, and then all that algebra, which is about a page. When we are done, I'm going to show you how this h sub s, with this specific form, comes about, and more importantly, what's the origin of this frictional head loss, and how it ties in with second law of thermodynamics. So that's the big picture. Question before I do the deep dive. So what I have done on the board higher, I cover it up. Can you see in the back? Can you see in the back? How's that? Good, thank you for letting me know. So, system equation. What I have done is the equation I have covered by the screen. Instead of just Q minus W equal to capital E, I take the weight equation, which is differentiated with respect to time. Are you okay with that? All right, so I have now a weight equation for first law, and like I did before, I introduced the capital B to become a total energy that consists of internal, kinetic, and potential, all per unit mass basis. And here is my Reynolds transport equation, just like I did behind the screen. And what I do here is now approach to get my first law for a control volume. And that is all I can get out from the Reynolds transport equation. No more, no less. You set that on the system on the left-hand side here. The transport equation of Reynolds allow me to relate that to the fluxes of energy. The term that is inside my control volume, rate of change with respect to time, which is this first term, and the energy fluxes leaving and entering my control surfaces. Just like continuity and just like momentum, it reads the same, except now it's switched to energy. Any question on that? Does that make sense to you? Okay? So this may be what you have seen in your thermal, and this is what you use for first law in analyzing a control volume. We're going to make some assumption to make the form more applicable to fluid flow, and specifically fluid flow in a pipe. That's the equation behind the screen here. Yes?
So in the equation we were working with earlier, the Reynolds transport, it's the rate of beta system, right?
Yes.
And if we're using the small e, the energy per unit
Yes.
there, why in this equation is it total energy, not per unit mass? We have d capital E over dt.
You mean this equation here?
Right. Because we're setting dE dt equal to the Reynolds transport theorem. So
Yes.
we're using small e in the right side and large e in the left side.
I don't think I make any mistake.
I'm just confused as to why that is. I'm not saying you're making a mistake, I'm just not sure why we're using.
So instead, you're saying this should be a small q and small w? No, this is, okay, so let me break it up. Don't look at this side yet. Don't look at this side yet. Are we on the same page up to this point? Because this equation is exactly the same as what I started for a system. Right? Everyone understand the question? Okay. Now take the Reynolds transport equation in here, whereby I replace this capital B with what? No, capital B. No. This capital B is now become my capital E. I think that's where the confusion is. Okay? On the left-hand side, this is capital, total energy, not per unit mass. But then on the right-hand side, the beta is per unit mass. I think I know what you're asking. But that you misinterpreted the Reynolds transport equation. So I think it's a little detailed question if you, I don't want to confuse the rest of the class, but this is correct. Okay? But fair enough, I don't want to drill on this, but if you have a question, come see me after the lecture. So the additional assumption I make for specifically pipe flow, so I can at the end get the equation behind the screen with all the shaft work in head and the frictional head losses, I'm going to assume no heat transfer, which is very fair for flow in the pipe. No significant heat transfer, and even in machinery like pump or turbine, external heat transfer is negligible. So that will be made so the Q becomes zero. Steady, we always do steady problem. Forget the integral, assuming uniform inflow and uniform exit flow, even though it's viscous. Okay, even though there are no slip boundary there, but we're just going to work with average velocity to make this problem simpler. And throw in the incompressible assumption of constant density, the equation now become the first law for a control volume can now be written as this, where the heat transfer Q disappear, the work now is per unit mass. I have then from my Reynolds transport equation, all this is equal to the change in total energy. Do you see that? Any question? I know, I see a lot of blank faces. Are you on top of this? You okay? All right? What becomes interesting is this so-called work. For a control volume, take on a different aspect. What do I mean by that? The work into my control volume, like defined in here, which can be a turbine or a pump, consists of two pieces. The first one is obvious, the shaft work. So if it's a pump, I'm running it with the motor, the electrical power to run the pump is added to the fluid. Or if it's a hydraulic turbine, I'm taking energy out from the water as it goes through my turbine. So that's what I call now the shaft work. Work transferred in and out of fluid due to a machinery penetrating into my device or my control volume. So those are the typical control volume of pump, turbine, compressor, etc. The other one, which is not obvious, and you may see this in a different form in your thermal, you may be called flow work or pressure work. And it comes about because now we are not dealing with a fixed mass in the system. We are now dealing with fluid that enter and leave my control volume. It turns out as those fluids interact with my device in the import and the exit port, that motion can create work that we call pressure work or flow work. And that can be represented. That can be represented from thermodynamic principle. Instead of using the internal energy, that flow work, which is pressure times a specific volume, can be replaced by enthalpy. So H is now not the height, H is your enthalpy. How is enthalpy defined? Just as, anyone remember that? What is H equal to? U, internal energy, which is in here, plus what now? PV. That PV, pressure times the volume, is what we call the pressure work, or the flow work. And it comes about because of the motion of the fluid, which doesn't happen in the system, coming in and leaving my control volume, leaving my device, leaving my turbulent, leaving my pump. So that work in my control volume through the Reynolds transport equation had taken on now a new meaning. I have to account for the machinery work through the shaft, and I have to replace internal energy with enthalpy. Enthalpy. We touch on that in 21, 24, but at the time we just tell you, take it as a medicine, don't ask me why, just use it. So here's why. The fact the motion of the fluid entering my device in the control volume resulted in some pressure or flow work, and it's being represented by P times specific volume. And hence you replace the internal energy with enthalpy, H, not height. Do you appreciate that? Do you understand what I'm saying? Have you seen that in thermal? That when you go from your system first law to a control volume first law, you replace U by H? Did you ever ask why? No? Here's why. Question on that detail. So my next job is then take my original equation, which I have recopied here. This is the same form for the PI page. And I'm going to replace the work with the shaft work, and I'm going to replace the U, internal specific energy, with my specific enthalpy. H2, H1. Again, this is not height. I want to make sure you don't get confused with the nomenclature. This is what you have done in your control volume thermodynamic. Am I correct? This is what you use. With the exception, you may have heat transfer to look at work through a boiler, or a turbine, or a compressor, or an IC engine. Have you done all those problems? Yeah, in thermal? So I'm bringing fluid and thermal together in some coherent way. Question on this before I move on, and we're getting a little closer, we're halfway to where I can explain to you how the H sub F comes about. This is closer to where the H sub S, or the WS comes about, right here. That's how it started, all right? So the next step is just algebra. I replace the H, enthalpy, with P plus PV, but written in a different form because of the way the equation is cast. So I have now the pressure finally appeared. And now my internal energy pops up. And we'll find out what that will lead to at the end, okay? So I have now something that I'm kind of resemble where I started. Pressure, velocity squared, and the gravitational term. And if I divide everything by G, no change in physics, just the appearance, I have now the equation in terms of height, head, which is what I gave you for the energy equation. And that's how it comes about. Do you see it? Question on this, can you explain all the terms here? Do you understand what the nomenclature stands for? What is W sub S, small? What's the unit of that? What is the unit of W sub S? What is the W sub S in the energy equation I gave you last lecture? What is it in SI? Say it louder. Someone is mumbling. Are you sure? Kilojoule per kilogram? Yes. Kilojoule per kilogram. So if you can answer that, you're on top of this. If you don't, please ask. And what's the unit of this equation? No. What's the unit of this equation? If you have to think, I'm in trouble. Length, head. head. Yes?
Why is that? Can you explain that? I'm sorry. Oh, is it because of the Z?
Yeah, because of, thank you, thank you. So be smart when you have an equation that some of the terms just totally out of whack. Even if I look at this, this term, I have no idea what it represents. I look for the simplest one. In this case, I look for the Z. Because I know that's the height, that's the head, that's the length. And everything has to be in the same unit, length. Right? Be smart. Law of common sense. Any question before I continue? So we are finishing close to the punchline. So all I'm thinking now is called head. When you work in a power plant industry and you go buy a pump, people will tell you this pump can give you a head of 100 feet of water. That's what it means. The 100 feet of water is tell you how much energy the pump is capable of putting into the water per unit. What? Weight. Very good. So by telling you that, it sizes the pump for you. Right? Because it tells you how much energy has to be put into the water per unit weight. So that's why it's emphasized the physical interpretation. Yes?
Are you assuming no heat transfer to cancel out the U2 and U1?
No, that has nothing to do with canceling U2 and U1. First of all, the heat transfer is totally unrelated. But for most fluid problem, heat transfer is really inconsequential. So we can always throw it out. Throw in the pipe in the HVAC, heating a couple of degrees inconsequential. U2 and U1, I have not done anything to it. Don't touch it yet. That's the punchline. That's all that half an hour spent is to get to what happened to that U2 and U1. They stayed. I didn't get rid of them. Okay? And that's the punchline at the end. So, now you see how this equation comes about, which we finally put it in a form that is similar to the energy equation behind the screen. I have now this Ws over G. So this is what we call H sub S. S stands for Sheffield. What I don't have is where is the H sub F? Can you make a guess? Where is the H sub F? How do I get rid of U2 and U1, which doesn't appear in my energy equation? Well, it turns out if you rearrange this one more time, so this is something you can read on your own, but the most important part is, here's a punchline. I'm going to get the equation in the exact form that I have behind the screen, which is why I start the lecture today. I have identified all these head terms, look like Bernoulli, but not Bernoulli, the point 1 and the point 2. I show you how this chef work comes about. The only thing that is missing is I don't have H sub F. So what is H sub F? U2 minus U1 divided by G. That is now the punchline. H sub F is nothing but U2 minus U1, the exit internal energy minus the inner internal energy divided by gravity. For an ideal gas, how do you approximate U internal energy? For an ideal gas? CV delta T, very good. CV delta T. So here's how second law, entropy, availability all comes into this discussion now. This so-called frictional head loss, friction, losses, is nothing but a representation of the increase in internal energy, U2 being higher than U1, due to friction. How does that happen? Take your hand and rub it. I'm doing work, right? I'm doing work. How does your hand feel as you keep rubbing it? You get warm. Due to what? Friction. Friction. My work of moving the hand, the energy, is now used to overcome the friction, which happened to raise the temperature, all in line with the internal energy. Once that temperature is raised, can you get the work out of my higher temperature from my hand? No. Sorry. I conserve first law, but there's no way you can recover this energy. It's gone. It's the loss of availability. is the increase of entropy. So this U2 minus U1 represent the irreversibility. Energy is conserved, but it's gone. It's not the energy coming from the exhaust of the muffler of the car. It's warm gas. To try to recover that, good luck. It's used nothing but to heat the environment. This energy, this heat, is nothing but to increase the entropy of the universe. They're gone. Say goodbye to them. Do you understand all this thermodynamic? Second law, entropy, availability, that entropy will only go up and up. This is what happened. The friction, the power to overcome the friction is the loss of availability. They're gone. Cannot recover it. Yes?
So if we can't recover that energy, does that mean like your body is losing energy when you
The
rub
what?
your hands? Like, is your body losing energy when you rub your hands together?
Mhm.
Or-
No, I'm using my energy. My energy comes from the food that I took, right? So when I rub my hand, I'm conserving energy from the food intake I have, and I create some energy of rubbing my hand, which generate nothing but heat, but no useful work. That heat is just like the greenhouse effect. That heat is only used to heat up the universe, right? So energy is conserved, but the waste heat is heating up the atmosphere. Just like the exhaust from the automobile or exhaust from a gas turbine engine, that hot plume. The energy is there, but you can't get it back. It's wasted. That's entropy. And that's how this H sub F comes about. And this is why the H sub F is always what? Positive? It's 0 or negative? Always positive, because the entropy can only go up. Yes?
Could anything other than, like for fluid flows, could anything other than friction cause a change in internal energy that would contribute to the head loss?
Not unless you start adding heat transfer.
Okay.
The answer is no. The only thing that happened here is friction. The only best case scenario for you is you neglect friction. All right? Then by chance it becomes Bernoulli. But I don't want to use that term.
So if you had heat transfer, would there just be like another head term for?
Yeah, you will have another term that represents the heat transfer, but that's not conventional, and that is not, you will not use this form of the energy equation for anything that has heat transfer. This is purely for fluid flow in the pipe. Right? Very simplistic, but very practical problem that mechanical engineers do all the time at ExxonMobil, et cetera, et cetera. Do you understand the whole big picture? I spent, a good part of 40 minutes on this, so it is important. Yes?
So if you say, for example, that a pump has 100 feet of head, what does that mean physically?
So if I sell you a pump and say this pump is capable of putting in 100 feet of head, that means when you hook it up to a power supply, and let's say you draw 100 kilowatts, and you have water going in and water going out. The water come out from the pump has added power or energy to the degree of 100 feet per weight of the water. So it directly relates to how much work or power can be transferred to the fluid. And if it's a turbine, it's the opposite. So that head has some really important implication. It is an indirect reflection of how much work or energy or power can be transferred to the fluid. And that's why in layman term, in sales of pump, they don't use kilowatt or horsepower of the pump. That's actually very odd. You just talk about headwise. Okay? And so that's why people use that. Questions? Yes?
So would you use like the mass flow rate to translate the head into power, or how?
I'm sorry?
Would you use the mass flow rate to translate the head into power?
Yes, it's behind the screen. That's why I reminded you. When I pull up the screen, I will revisit that. The answer is yes. So the head, if you say I cannot put myself on the head, then you use that power equation, which is m dot, mass flow rate, times specific work per unit mass, which relate to the head. So that equation is critical to actually relate all this together to get power consumption, right? So I hope you appreciate how all this, it's a big circle, fluid and thermal are coupled. You know, we just go around and complete that circle, right? Okay, so before I put the screen up, I want to take a look at the Moody diagram. And some of you, I hope actually all of you, have seen this in 21-24. And what I'd like to do is to point out some of the subtlety of this graph. And then also, by way of example of the gasoline pumping, show you for one time how to read the graph correctly. So this is the most I can expose the graph. So have anyone here not seen this before? Good. Okay, so Moody diagram, internal pipe flow, is a chart developed by, obviously, Mr. Moody. And he did an experiment, just like your homework due today, which is you calculate the friction factor based on inches of water loss in a flow system where different velocity was given, right? That's the homework due today, am I correct? So we obtain an average friction factor for that set of data. That friction factor is used to create now the y-axis. So if you're Mr. Moody, you have done the experiment, either in air, in water, or in oil, but this is how you get the friction factor. You measure the pressure loss, and then you use the formula, we define the friction factor, and you calculate that, and that's get your data point at a specific Reynolds number, 1 point.